Hi, welcome to Electric Fields Part 2, representing electric fields. So electric fields are pretty much everywhere. They're sort of like gravitational fields, but we don't often notice them. But in terms of physics, they're just about everywhere. Your cell phone has them, cell phone towers have them, power lines are surrounded by them, radars, everywhere we've got them. We've got electric fields going through us right now. So how do we represent these electric fields? And how, as physics students, would we draw them? So an electric field is defined as an area in which any electrified object will experience a force, no matter how small. So we're not necessarily talking about large forces. Before we do that though, let's just look at electric fields being used as art. You wouldn't think so, but this is what some artists have done, is they've recognised that around power lines, so they've got to know a little bit of physics before they can do this, there's an electric field, and if you arrange fluorescent tubes in a correct pattern close to these power lines, they'll light up with a fairly faint glow, but at night time you can see it's fairly bright. And this is another, what's called an installation, where all these are fluorescent tubes lined up, and it's starting to get dark and it's starting to look a bit impressive. Now you could do this anywhere where there's fairly powerful or high tensile or high voltage power lines. And there's another shot of it as well, and this is a little bit more of it. I think it's a pretty good idea. And some other people did some other different ones, and these ones did them across a road. Pretty cool. So, representing electric fields in the physics way, not the artist way. So, what we have are called field lines, electric field lines, and they never cross. So when we draw them, we make sure they never cross. The electric field lines have a direction, and they are directed from the positive charge towards the negative charge. That's how we define their direction. And so, the direction is the direction a positive charge, if we imagined a positive charge, would experience, so it would be attracted to the negative. Electric field lines will enter and leave any charged surface at right angles, so they can't leave at an angle. And so here what we've got is a vat full of oil, and in the oil they've put a whole lot of hairs, and this is an electrode that has a charge going through it. And these hairs line up much like with the Van de Graaff generator. All the electrons are going along the hairs, and so each hair is repelling each other because of all the electrons on it, and they distribute themselves in these sort of spoke-like pattern, and that would be a representation of the electric field. If we had two charged plates or poles in this case, we would get an electric field between the two, so one must be positive and one must be negative, and we get this curvature happening. Okay, so let's just look at the last one, and this is what it looks like with two plates. So it's sort of like plates like this. They've got a potential difference between them, so effectively they're hooked up into a circuit, but no currents flowing through, but there is a potential difference between the plates, and so you get an electric field between these two. And so the hairs here are lining up, and you can notice that we would have what's called a uniform electric field in this area here, and then the field extends outwards. And so this is how we would represent it if we draw it. Here's a positive charge, and so the electric field is out from a positive charge. So imagine you put an imaginary positive charge there. The direction you draw the electric field is the force in the direction that that imaginary positive charge would experience. So in this case, away from this one. And conversely, for a negative, the field lines go towards, and notice they don't cross. Notice also that as you get closer to the charge, the field lines are denser, which means that you have a stronger electric field. So we're trying to represent all those sorts of things. Here's some more simple ones up here. So it doesn't matter how many field lines you draw, you're still trying to represent an even pattern, and that the electric fields get closer and the direction. Here's a representation of that one we saw before, where you have your field lines. Notice they don't cross, and where you have more field lines, the electric fields are stronger. Where you have fewer, the electric field is weaker. And this is two positive charges, so they repel, and they repel away from each other. And so there's an area in here where there's very weak electric field, virtually none there. And it's symmetrical also, you notice. Again, more diagrams. And this one, we're showing this one just to show what happens with some plates. So we can have two plates and have an electric field between them because there's a voltage between the two plates. Doesn't have to be a current flowing between the plates, just has to be a potential difference or a voltage. Basically, you hook it up to a battery or something. And as soon as you do that, you generate an electric field. And between these two plates, one plate will be negative, one will be positive, and the electric field will be uniform between the plates and non-uniform outside. This is a non-uniform field, this here is a uniform field, and they haven't put their arrows on it, but if this is a negative plate and this is a positive plate, we use an imaginary positive charge. Positive charge would be attracted to the negative plate. So these guys here, let's draw it because we can. They're going to let me. Here we go. Oh, it doesn't want to draw. There we go. They should be positive like this. There we go. And that's what our electric field should look like. So make sure you put arrows on them when you can. Right, now let's move on. And more, here's our plates again, not showing the end, but showing a uniform field. Here's a plate and a point, and so again, you're drawing your field lines. More representations, what's called a radial field, uniform field, which is what we use for a lot of experiments because the uniform field is consistent, has a lot of uses for us. And these are out of our textbook. And here's a complicated one where you've got a negative, a positive, and a positive. So the field lines go towards the negative, but the positive and positive repel. So you've got to make a combination of those. Bit tricky, but you should get an idea about it. Now, 3D field of B. I've got a little animation here that should magically appear when I press this button. There it is. So this is a little video of two point charges and a three-dimensional representation of the field. So just to reinforce that this is three-dimensional, although we draw it in 2 dimensions, electric fields are three-dimensional. Let's get rid of that one. What's next? And then a mobile phone. So a mobile phone generates an electric field, and this is what some guys have modeled it as, and that should be playing for some reason. Here it goes. So here's your head. Mobile phone's that blue thing, and you can, and this is just a simple modeling in 2 dimensions of a slice, and you can see the variation of the electric field. And what you can also see is the electric field does actually go into the brain a little bit, and that's what they were trying to highlight. And whether or not mobile phones are dangerous for you or cause health problems is a hotly contested topic, which I haven't got time to go into. So let's get rid of that one, but we can talk about that in class certainly. And so the next video is we're going to look at how we determine the electric field strength. Cheerio!